Good afternoon, everyone, and welcome to the second episode of the JuiceFS Office Hours. My name is King, your host. Thank you very much for joining us as we dive into some exciting results from the storage performance world. Just as last month, the MLCommons released the highly participated MLPerf Storage 2.0 benchmark results, and I'm thrilled to share that JuiceFS not only participate in several code benchmarks, but also successfully demonstrated our capability to meet utilization thresholds across demanding large-scale AI workloads. For those who are unfamiliar with the MLPerf, it is a industry gold standard for measuring ML system performance. And these storage benchmarks are crucial to understanding how different file systems handle the intensive data requirements of modern AI training pipelines. So today, we are going to pull back the curtain and show you exactly how we achieve those results. We'll walk through the testing methodology, the specific optimizations we implemented, and perhaps the most valuable, how our performance compared to other storage systems in the market. Insights that can directly influence your own architectural decisions. So we will invite our core engineering involved in this MLPerf 2.0 test, Fei Hu, who will spend in the first 15 minutes or so in technical deep dive, and then we will open it up for live Q&A. So without further ado, let's welcome Fei Hu. It's all yours.
Okay. Now, good morning and good afternoon, everyone. And thank you for joining the JuiceFS Office Hour. My name is Fei Hu, and I am a system engineer at JuiceFS. Today, I'm very excited to take you through our journey with MLPerf Storage v2. We'll be diving deep into the performance insights we gained from this rigorous benchmark. More importantly, I will share the specific optimization practice we implemented to push the boundaries to what's possible. This will be a focused 15-minute presentation, and we will have a live Q&A session right after. So please, as we go along, feel free to think of any questions you might have. So before we dive into our specific results, I want to briefly introduce the organization behind this benchmark, MLCommons. MLCommons is a global AI engineering consortium, and its strength comes from collaboration. As you can see from the logos, it's a massive collective effort, bringing together over 125 members from across the industry and academia. This includes tech giants like Google and Meta, hardware leaders like NVIDIA and Intel, innovative startups, and top universities. The core mission of MLCommons is to accelerate AI innovation through standardized and transparent measurements. They achieve this with MLPerf benchmarks. MLPerf has become the industrial gold standard for evaluating the performance of AI systems. It covers the entire AI lifecycle, from training and inference to, crucially, of our topic today, storage. So when we talk about our performance in MLPerf storage, we are not only talking about an internal or custom test. We are measuring JuiceFS against a rigorous, peer-reviewed standard developed by the world's leading experts. This ensures the results are credible, objective, and truly relevant to real-world AI workloads. So what does the MLPerf storage benchmark actually test? It's designed to perfectly replicate the demanding environment of a large-scale, multi-client distributed training cluster. To do this, it uses a suite of 4 distinct and challenging workloads, each designed to stress the storage system in a different, realistic way. Let's quickly walk through them. First, we have image segmentation for medical imaging. This workload uses large 3D volumetric data with samples around 140 megabytes. It simulates high throughput sequential read, a test of how fast the system can deliver large files. Next is the classic image classification workload. We are dealing with a massive number of very small samples in each large file, about 150 kilobytes each. This is a brutal test of a storage system's metadata performance and its ability to handle high concurrency random reads. This is often a major bottleneck for traditional storage. The third workload is from the scientific computing domain, specifically cosmology. Similar to image classification, it floods the system with a concurrent read request for a lot of small files, putting heavy pressure on random read capabilities. Finally, is LLM checkpointing. With a model like Llama 3, this is a write-intensive workload. It simulates saving massive model checkpointings during training. This tests the system's concurrent write throughput at a massive scale. For our submission, we choose to focus on 3 read-intensive workloads. The reason is that JuiceFS write performance is directly influenced by the network bandwidth to the backend object storage. So as you can see, this benchmark is incredibly comprehensive. A storage system that performs well here has to be a true all-rounder, capable of handling the full spectrum of modern AI or machine learning I/O patterns. Here you can see the competitive landscape for MLPerf storage, which includes many major industry players. We are listed right here in the cloud and shared file system category in the first line. The key takeaway from this slide is the network layer. We specifically benchmarked JuiceFS over standard Ethernet because this is the most common and readily available infrastructure, especially in the cloud. This stands in contrast to many other solutions that rely on expensive, specialized networking, like IB or ROCE. We will show how JuiceFS provides top-tier performance without needing exotic hardware. It's a powerful solution designed for the cloud infrastructure you already have. So before we look at the numbers, it's crucial to establish a framework for how to properly evaluate them. The MLPerf storage benchmark isn't about one single hero number. It's a test showing both scale and efficiency. There are 2 primary criteria to consider. First, GPU utilization and scalability. This is the most important one. The benchmark has a strict, non-negotiable rule. The storage system must keep the GPUs busy. This means maintaining over 90% of GPU utilization for the 3D-UNet and ResNet 50 workloads, and over 70% for the more challenging CosmoFlow test. This rule ensures that the storage is genuinely keeping up with the compute. So with this high utilization as our baseline, the key metric for performance becomes how many GPUs can the storage system effectively support. A larger number of supported GPUs means better horizontal scalability. And the second criterion is resource utilization. Scalability is great, but we also need to be efficient. How well is the storage software using the underlying hardware? For this, we look at the NIC bandwidth utilization. The NIC, Network Interface Card, is the physical gateway for data flowing to the GPUs. If we can achieve high utilization of the network bandwidth, it means we are pushing the hardware to its limit. High NIC utilization directly translates to better efficiency and greater cost effectiveness, as you are maximizing your hardware investment. So as we move to the results, please keep these two questions in mind. Scale. How many GPUs did we support while keeping them busy? And second, efficiency. How many of the available network bandwidth did we use? With that framework established, let's look at the JuiceFS result. Now for the result, which I will summarize here before we dive deeper into each one in the next slides. In short, JuiceFS excelled across 3 workloads. For the large file sequential read 3D unit test, we achieved a massive read bandwidth of 108 gigabytes per second. On the large file random read ResNet 50 test, we delivered 90 gigabytes per second with extremely low latency and high IOPS. And for Cosmos Flow, the key scalability test, we successfully powered a large cluster of 100 H100 GPUs. The high-level takeaway is clear. JuiceFS delivers top-tier performance across the entire spectrum of AI read patterns: high throughput, low latency, and massive scale. Now let's take a closer look at what's behind these numbers, starting with 3DUNet. Before we dive into it, let's recap the fundamental challenge that every storage system faces in AI training. This Unit 3D chart perfectly illustrates the core problem. On the horizontal axis, we have the number of GPUs, and on the vertical in their utilization. Look at the left side of the chart. When you have a small number of GPUs, the storage can easily keep them fed. The GPU utilization is near 100%. This looks great, but it's inefficient. Your powerful storage hardware is mostly idle, and you are not getting your money's worth. Now, as you add more GPUs and move to the right, the demand for data grows. The storage system works harder, and its bandwidth is being used more and more. This is the balancing act we want. But eventually, you will hit a wall. This is in this example, right around about 100 GPUs, the storage system bandwidth is completely saturated. It cannot physically deliver data any faster. The moment that happens, GPU starts to wait for data and their utilization plummets dramatically. This is the storage bottleneck in action. So the game we are playing and what MLPerf measures is this: how far to the right can you push on this chart? What is the absolute maximum number of GPUs can you support while keeping their utilization above that criterion 90% line? This number is the true measure of a storage system's effective performance and scalability. This context is key to understanding our results. Now let's do our first deep dive into 3DUNet results. As remember, this workload tests to test the system's ability to handle high throughput sequential read of large files. Please direct your attention to the bar chart. On the far right, you see the result for JuiceFS. We achieved an incredible read bandwidth of 108 gigabytes per second. But what's even more important is the number on the top, 86 and 86.6%. This is our network utilization. This means we were using nearly 90% of the physical network total capacity. In an ideal world, the software should be so fast that the hardware becomes the only limiting factor. And that's exactly what we have demonstrated here. The high efficiency translates directly to better cost effectiveness. You get the maximum performance from the hardware you are paying for. Now let's look at the competitive positioning. The other bars representing other Ethernet-based submissions. As you can clearly see, JuiceFS delivered the highest absolute bandwidth of all participants in this category. And just as importantly, we also achieved the highest network utilization. If you look at the other results, you will notice a larger gap between their used bandwidth and the total available bandwidth, which might indicate a software bottleneck. So the conclusion for this workload is simple and clear. JuiceFS provides the best performance and the best efficiency in this class. This is made possible by our distributed caching, which we will touch on later. For a complete picture, let's quickly look at the results from vendors on specialized IB networks. You will notice that the total bandwidth numbers here are much higher. Also, this specialized hardware comes with significantly higher cost and complexity. So this isn't direct comparison. Our main focus is to deliver the maximum performance on the standard, cost-effective Ethernet that powers the vast majority of data centers. With that context, let's move on to the next challenge. The next is Cosmos Flow, the ultimate test for scalability. This workload is all about handling a massive number of small file reads. It's a pure test of metadata performance and low latency data delivery. And the results speak for themselves. On the right, you can see JuiceFS support a massive cluster of 100 H100 GPUs. Compared to other solutions, this isn't just a lead, it's a massive leap. So why do you win so decisively here? It's our core architecture. We have two keys to success. The first is our high-performance metadata engine. Easily handles the pressures from millions of files. And the second is our low-latency distributed cache. Ensures data is delivered to the GPUs instantly. The takeaway is simple. For massive scale training on small file datasets, JuiceFS is in a league of its own. Finally, for Cosmos Flow, let's put our results in the context of specialized IB networks. As the table shows, IB systems achieve a larger scale. This is because Cosmos Flow is extremely latency sensitive, and their hardware provides a significantly advantage. But this highlights a choice: specialized, high-cost infrastructure vendors versus standard commodity infrastructure. Our result of 100H100 is the top performance on standard networks. With this, we have pushed the commodity infrastructure further than anyone else. For our users, this means getting the most scalable solution without a costly and complex network overhaul. Now let's summarize the next workload, ResNet 50. It's a tough challenge for any storage system. The challenge is its I/O pattern, intense high concurrency random read inside large files, which demands massive IOPS. Our solution delivered on three fronts. The first, massive scale. We supported 500 H100 GPUs, the most in its category, while delivering the highest data throughput. And second, superior efficiency. As the chart clearly shows, we achieved 72% network utilization, far surpassing other solutions. This proves we make the most of underlying hardwares. So how did we do? That brings us to the caching advantage. Our distributed cache here is the key. It delivers the massive IOPS needed to satisfy the intense random read requirements of the ResNet 50 workload. This is how we keep the GPUs fully saturated with data. This unique combination of scale, efficiency, and architecture is why JuiceFS excels. Here is a quick look at the system topology we use for MLPerf benchmark. Let's break it into three simple layers. At the bottom, we have our high-performance metadata engine for metadata, and GCS as the durable backend for all the data. In the middle is the core of our performance, the distributed cache group. This is an elastic layer of nodes that can be scaled on demand to meet any performance target. At the top are the clients. We use Fuse clients here, the GPU machines running on the actual training workload. The entire environment is connected with high-speed 100 Gbps networking. Before the test, we performed a quick cache warm-up, loading the datasets from GCS into the cache group. This ensures the GPUs get maximum I/O performance from the very start. So, to summarize, how did we achieve these leading results across different workloads? It comes down to the core features of our architecture. Shown on this slide, we tackle performance in two distinct ways, one for metadata and one for data. First, for metadata, we combined a high IOPS metadata engine with client-side metadata caching. This powerful duo crushes metadata-heavy workloads, which is why we achieved the best Ethernet result in the CosmoFlow small file benchmark. And the second, for data, the powerful house here is our distributed cache cluster. This is an elastic layer that delivers incredible performance. We have clocked it at a maximum of 1.2 terabytes per second in our own tests. This cluster efficiency is what led to the highest network bandwidth utilization in 3DUNet, and its massive IOPS capability is how we delivered the best IOPS results in ResNet 50s, demanding random read scenario. Ultimately, it is this dedicated optimization for both metadata and data that allows JuiceFS to deliver ultimate performance, no matter what the workload is. So that concludes our deep dive. We've seen how JuiceFS unique architecture delivers leadership in performance and scalability, especially on the standard, cost-effective infrastructure that powers most data centers today. We are an open source project, and we invite you to get involved. Please consider starring us on GitHub, joining our community on Slack, and following us on X and LinkedIn by scanning the QR codes. Thank you. I'm now happy to take any questions. Don't forget to subscribe our YouTube channel. Thanks for listening.
Okay, thanks,
Okay.
Fei Hu. Now it's live Q&A time. So you can post your questions in our YouTube channel, in the live chat, or in a Slack channel. Oh, actually, I have a question for you, Fei Hu. So all these the chats, the results we can see from the MLCommons website, right? Oh, you muted.
Okay, yes. It's all available on the MLPerf Storage official site.
Cool.
Yes, and our setup is available on the GitHub of MLCommons. It's all available on GitHub. Okay.
Right, as well as the other participants for this MLPerf 2.0 test, right? So you can see all the setups from Oracle, from Huawei, other participants. Right.
Yes. Yes.
Cool. Thanks. Make sure you guys can check out Google Easy to direct to the site. Okay, let's conclude today's office hour. Thank you for watching, and see you guys next time. Take care. Bye.